In this video, we're going to continue on with Chapter 9, and by the end you should understand why we're using the t-statistic, why we're moving from z-scores and using a z-test to doing a t-test. We'll identify the formulas that are associated with the t-statistic, which hopefully you'll notice are not much different than those associated with the z-test. So why use a t-statistic as an alternative to the z-scores? The z-scores basically require more information than researchers typically have available. It requires a knowledge of the population standard deviation, which up until now we've been given. Researchers really only usually have the sample data available. So the t-score that we're going to come up with, the t-statistic, might be considered kind of an approximate z. So the estimated standard error, notated as this for the sample, is used when our population standard error of the mean is unknown. So again, this estimated standard error is used as an estimate of that real standard error when the value is unknown. So we use s squared to estimate, which is our variance, to estimate for the sample, to estimate our population variance. An estimated standard error, then, this formula looks like this, and it should look pretty similar. All we're doing is taking the sigma and replacing it with an s. And remember, we said we use the sigma, we use that Greek notation when we're talking about a population, and we use lowercase alphabetic letters when we're talking about a sample. So this formula should look pretty similar. We haven't looked at this one in a while, but it's just basically the idea is that this is the square root of this formula. So a little more review, just to make sure that we all know where we're going from and where we're coming from and where we're going to. We already said the sample mean estimates the population mean. The standard error describes how much difference is expected between the mean and the sample mean and the population mean. So again, that standard error, it's the expected variation, and the mean, sample mean minus population mean, is the amount of difference that was detected or was measured. So in terms of calculations, this is what we've been working with. That's the population, and this is what we're going to be working with for a sample. So again, these alphabetic letter S is just replacing that Greek sigma. So don't worry, really not new calculations, just different letters for the same thing. So again, just to kind of compare things side by side, the z-score quantifies inferences about a population, whereas the t-statistic tests hypothesis about an unknown population. So here, the standard deviation is unknown, and possibly also the population mean is unknown. Whereas for the z-score, they're known. So that's kind of what one of the main differences is why we are using this t-statistic now. The z-score uses the standard error. The t-statistic uses the estimated standard error. For the z-score, we use the unit normal table. And for the t-statistic, we now have a new table that we're going to be using. It's the table of values for t. And it requires that we know the degrees of freedom. And so degrees of freedom is also something we haven't talked about in a few chapters. So we'll refresh our memory on that in a little bit. So this is the formula for our z-score that we've been working with. And this is going to be our t-statistic formula. So again, you see hopefully the similarities. This is just the measured difference from the mean, right? The sample mean minus the population mean. And here we have our estimated standard error. So for this, population information is needed. And for the t-statistic, that population information is not needed. So here again, just looking at the formulas that we had earlier, just reminding you, just kind of showing you again, this is the population information, this is sample, population, sample variance, and then degrees of freedom. And this is our estimated standard error. So this is our standard deviation, this is our variance, and this is the degrees of freedom. And you'll see here when we're talking about the sample, remember we use those degrees of freedom. One other thing to note is that when we're looking at our distribution, this dotted line here, this one here, that's the normal distribution. Now our t-distribution is a little fatter and a little wider than than the normal distribution. It approximates the shape of a normal distribution, but it's a little bit flatter, a little bit more spread out, and there's more variability in the tails. So this is a t-distribution for degrees of freedom of 5, so an n of 6. Let's see how the tails are a little bit fatter. It's a little bit flatter. The tail's a little bit fatter. The distribution peak's a little bit flatter. And the variance is a little bit bigger, so it's more spread out. As you increase your sample size, getting up to degrees of freedom of 20, you start to approximate the normal distribution a little bit more. Your tails aren't quite as fat, and your peak's a little bit higher. So t-distributions are bell-shaped and symmetrical. They have a mean of 0 just like our z-score normal distributions. The larger the value of degrees of freedom, the more closely the t-distribution approximates the normal distribution.